All right, so I got a green light, so I think I'm supposed to get started. So hey everybody, my name is James Sirota, and I'm here with Chester Parrott. We're data scientists from Cisco, and we're here to talk to you about anomaly detection on networking data. So in the next few minutes, this is the outline of our talk. We'll introduce our defense in depth approach to security analytics on top of big data platforms. We'll give you a brief overview of network anomaly detection and specifically volume anomaly detection and feature anomaly detection methodologies. We'll go through model architectures and common best practices for deployment, and we'll go through specific examples of deploying these models on top of our platform called Open Security Operations Center, also known as OpenSOC. And then at the end, if we have time, we'll field questions from the audience. So who are we? If you don't know who we are, we're a big data team at Cisco who is focused on applying big data technologies to security analytics. We have an open source project called OpenSOC, and we offer a managed security service around that open source offering. So today we're here to talk about network anomaly detection, but before we do, we wanted to sort of step back a little bit and describe how network anomaly detection fits into our overall analytics portfolio. So we have 4 distinct classes of analytics that we actually do. So the first class is misuse detection, which is comprised of basic signature matching and rules-based matching. And that sort of represents a legacy mindset. So that's where you have expert users or experts into how your networks work, or how your assets work. And these experts can create various rules. So we offer a distributed rules engines to load up the rules to start getting rule-based alerts, excuse me. We also offer integration with threat intelligence feeds, so you can get alerts from other experts on other systems and networks, so you can sort of get a benefit of collective intelligence. And we also offer static sandboxes, so if you have signatures for specific types of malware, you can explode files inside of these static sandboxes, and you can cross-reference them with malicious signature. So the second type of analytics that we do is intrusion detection. And that basically involves primarily unsupervised model to deal with sort of like an umbrella terms for generic threats. There are 3 kinds of intrusion detection that we do by analyzing network anomaly, which is the sort of the box we're going to talk about today. We also do log anomaly detection, which is it's sort of similar but requires a fundamentally different set of algorithms for analysis. And then finally, we do behavioral anomaly detection, which involves user profiling, asset profiling, and interaction between users and assets. So every time one of those profiles don't fit sort of our understanding of normal, we raise an anomaly based on that. On top of that, we deploy supervised classifiers, and the difference between sort of supervised classifiers and intrusion detection is the supervised classifiers are very highly targeted for specific and advanced kinds of threats. So for example, we decompose a lot of types of malware down to machine bytecode. We run model, or we do feature decompositions. We run models over that. So the kinds of things we're trying to model is how malware is trying to open command and control channels, how it tries to hide these command and control channels, how it tries to get at user data, how it tries to exfiltrate that data. And we have a variety of examples of these behaviors from our customer data sets as well as Cisco internal malware data sets. And we build very large and sophisticated training sets out of that data and train our supervised classifiers. And we deploy that in very targeted fashions to look for very targeted behaviors. And finally, the last box, and we just recently started doing this, and we're still in very early stages, is something we call look-ahead analytics. And what that involves is sort of looking outside of the customer networks to see if there's any threats that we can associate to specific asset classes or customer classes, and if we can get any sort of actionable intelligence out of that sort of external data set. So like I said, we're still really early in this, but we're hoping to produce something actionable in sort of probably in the near future. So now let's do a deep dive specifically into network anomaly detection. So we view network anomaly detection as two distinct sets of algorithms. One that deals with volume-based anomalies, so they're basically an umbrella term for any type of anomalous traffic pattern. And the second time is feature-based anomaly detection, which is where you actually look at features in the messages and then key off your anomaly detector based on interrelationships between these different features. And specifically, we implement 8 different classes of anomaly detection between these two classes of anomaly detectors. Today, we're going to talk about 7 of them. We couldn't quite squeeze in the last box. It's quite a lengthy process to explain those models. So we'll probably do another presentation as a follow-up to this, where we explain the last sort of a more advanced type of model. So when would you use volume-based detection as opposed to feature-based detection? So if you have an encrypted traffic where you can see how many packets you're taking in, but you can't quite see inside, into the payload of that packet, everything else is encrypted. Obviously the most appropriate technique for you to use is volume-based methodology. The same can be said about machine exhaust data, where you get volume data for your CPU utilization, memory utilization, I/O, things like that. Obviously, the best type of technique to use for that is volume-based anomaly detection. On the flip side, for deep packet inspection metadata, the best methodology to use for that would be feature-based detection. Obviously, because with DPI data, it's very feature-rich, but it only represents a subset of the actual networking data, so you couldn't quite key off a volume anomaly detector on it, but you could do very well with a feature-based anomaly detector. And today, the example we're actually going to use is the row packet header, or row packet plus header metadata, so the standard 5-tuple. And the reason why we're using this example is because you can key off both volume anomaly detection and feature-based anomaly detection on this type of telemetry. So it's just sort of a very simplistic telemetry that makes sense for sort of explaining the concept for this presentation. So what is anomaly detection? Anomaly detection for us is a 3-phase process. So the first thing we do is we stream a whole bunch of unstructured data from the data center, whatever topologies we can get our hands on. The next step is to identify as many anomalies as we can based on some historical context, so everything that deviates from normal. And the key here is to look at as many places as we can in as many different ways as we can to identify these anomalies. The next step is, once you sort of have this conglomerated set of anomalies that you've identified, is you try to classify them, right? So when telemetry A has an anomaly, telemetry B has an anomaly, in conglomeration, what does that actually mean? So we have the anomaly identification phase, which is a supervised phase that has a training set associated with, whenever a certain set of anomalies happen, in specific sequences, the classifier sort of makes an assumption. It's what's called the multi-class classifier. Tries to figure out what kind of anomaly you're actually dealing with based on sort of various micro anomalies. And then the last phase is examine and reinforce, where we have a human in the loop that actually looks at the kind of alerts that the machine has produced and determines, if that's a false positive, true positive, and if it's a true positive, if the machine actually identified the anomaly correctly. And then so drilling deeper into these phases, right? So as I mentioned, phase 1, and by the way, in this presentation, the wizard sort of represents the wizardry of the model, so we're trying to sort of de-emphasize the wizardry that's going on, and we're trying to explain sort of in human terms what is going on in that box. And so, in very simple terms, the model takes in a whole bunch of unstructured data. It has, each model has some sort of understanding of what normal means, and it produces a variety of anomalies, a variety of different anomalies. And then what it does, it builds up sort of this temporary data set of all these anomalies. So this is an example of different kinds of models executing it against different telemetries, detecting different kinds of micro anomalies. And then, as you can see in the end, there's a class label where the model either guessed or somebody labeled, when you see this kind of anomalies, that means this kind of outcome, right? So it could be a false positive, it could be a true positive, and if it's a true positive, you label with what you think that attack actually is. And then what you do is, when you have a person look at it, every time the machine gets something wrong, you basically, you take that example, you correct it, and you append it back to the training set and retrain the classifier. So you essentially get a cycle of continuous improvement. So every time you reinforce or add additional values into the training set, the model becomes better and better and better. And the key is to include as many false positives as you can, right? Because with anomaly detection, it tends to produce a higher level of false positives than other types of algorithms because it's primarily unsupervised. And so by reinforcing sort of a lot of these false positive values, you stop the anomaly detector from becoming, what we call a spam bot, and it sort of keys only in the anomalies that you actually find important and want to be alerted on. So today, for some of the examples that we're going to go through, we're going to deal with just basic anomalies like denial of service, alpha flows, port scans, network scans, things like that. But we just wanted you to know that the algorithms that we're going to present today are actually applicable for detecting a lot more complex types of anomalies, maybe associated with worms, viruses, botnets, and things like that. But just to keep it simple and just to get the concept across, we're going to focus on these very, very basic types of anomalies. So the first class of algorithms we're going to take a look at is volume anomaly detection. And this specific class of algorithms is batch. So the model itself is compiled via batch, and then the scoring for that model is done in a stream processor. So the problem statement is this. So you're checking along on a random Tuesday. You're looking at your graph in the middle of the day. You have some that you think is an anomalous point. So how do you know if that is an anomalous point or if it's just something that's a part of your normal behavior? So what you do is the most basic way to do it is you separate your historical data into time bins for all of the days you have in history. So this plot demonstrates, week -1, -2, -3. So here we have 5 weeks worth of historical data. And we take a look back and we see what did we see historically that data to be in the previous days. We extract that data from a time series database. So we take it at a point and we look a couple of points backwards and a couple of points forwards from that point. We build a distribution out of these and then we analyze this distribution. So you can't see it well on this plot, but it's a box plot that basically means that your expected value is for that should fit into that box. And if you get anything that's outside of the box, it's an outlier and therefore anomalous. So this represents, for this particular value, you expect the value to be somewhere around 3, and you got something around 10. So it's more than whatever standard deviations above what you expect to see, so you flag it as an anomaly. So from the implementation perspective, it's the simplest algorithm to implement. On top of a MapReduce paradigm. So you do a map out of your time series databases, and you emit by asset ID, metric ID, and bin. And then your reducer, you emit by the same key, but what you do is you do a 5-point summary of the distribution where you expect that value to lie, right? So the 5-point summary, as you can see here, is a minimal, the first quartile, the median, upper quartile, and a sample maximum. And what you do is you take that data that comes out of your MapReduce job, you load it into a persistent cache. And so the example of a table would be, the table is labeled with the metric ID, which is, as an example, would be cumulative volume. Then you have your asset name, the bin, where the value fits, and then the 5-point summary of that value. And what you're then do is you start streaming telemetry into your model, and the model says, okay, this is what the data I have now, this is the data that I expect based on my historical understanding of normal. Do they match up? If they do, then it's great. If they don't, then you basically issue an anomaly. The second type of model, which is highly related, is a batch forecasting model. And so in this plot, you see, again, I'm checking along on a random Tuesday, and I have three historical Tuesdays archived in my time series database. So what I can do is I can take the 3 Tuesdays that I have, and I can use a forecasting algorithm, something like ARIMA or Holtz-Winters, and there's a bunch more that can do this. And I can come up with what I think the next Tuesday will look like based on the previous few Tuesdays I have in my archive. And what I then do is, as I chug along on that random Tuesday, as you can see, my red graph represents what I forecasted the traffic to be, and the blue graph represents what the traffic actually is. So as long as it's somewhere close, I'm okay. And then when you see the expected value sharply spikes down, but the actual value sharply spikes up, then I know something's wrong, so I raise an anomaly there. The implementation, again, is also really, really simple and really close to the normal C model implementation. So you map, you again emit asset ID, metric ID, and bin. And then in your reducer, you summarize what the expected value is and the standard deviation from that value. So the example would be the same table. You get your metric ID, your asset, your time bin, expected value, and standard deviation. And again, just like previously, you stream data into the model, obviously live in your stream processor. And the model says, okay, this is what I have now. This is what I think historically I should have. Is it the same? No, it's an anomaly. And from the implementation perspective, and this is an example of implementing this on top of OpenStack, but it should generally be the same for any sort of big data framework, is the first thing you need to do is you need to stream a whole bunch of data into a time series database so you're able to compute historical distributions or be able to forecast into the future by having enough historical data. So you run that maybe for a few weeks to make sure you accumulate enough data there. The second step is once you feel comfortable you have enough data, you run your MapReduce jobs, your Spike or your Spark jobs, you build up this expected values reference cache. Then in our case, you take the OpenStack framework that all it does is just does dumb streaming. What you do is you plug in the expected values cache to it. You plug in the corresponding model that works with that cache. And then after that, the model starts producing alerts. And in our case, it does it into Elasticsearch, but obviously it can do it into any type of historical store. So the second type, or the second category of anomaly detection algorithms are volume online anomaly detectors. And the key thing you need to do is you need to transform the data that looks something like the top plot into something that looks like the bottom plot. And the reason for that is once you start computing your anomalies or checking for your anomalies in your stream processor, the algorithms that you can use to keep up with the volume of data that's coming at you have to be very efficient. And because there's many of them running co-located, they can't use a lot of memory, they can't use a lot of CPU, so they can't store a lot of historical data to know if the anomaly they're catching is just based on some seasonal trend or it is actually a legitimate anomaly. And so this graph shows the graph on top, shows your typical networking chart where in the off-peak hours, you have sort of low levels of work being done or low levels of throughput in the network. And then when people come to work, the value spikes up, people go home, it goes down. Then the next day it repeats and repeats and repeats and repeats. And that is called seasonality. So there's a lot of statistical algorithms out there to deseasonalize the data. So what you need to do is you need to take something that looks like the top chart, deseasonalize it, and turn it into something that looks like the bottom chart. And there's another distinctly different set of algorithms to do that in the frequency domain, and Chad will fill you in on that a little bit later in this presentation. Other types of things you need to watch out for is trend. So as people install more software or you get more users, your networking usage incrementally creeps up. So you need to adjust for that too. There's seasonal variability as well, where in the periods of low performance you have fairly low variability, but when people start hacking in your network during the work hours, the variability spikes up. And also what we call evolution of regularities. For whatever reason, if there's a deadline or something, people will come to work early and leave late. So the curve will actually expand. And once you get it adjusted into something that should look like a flat line, then you can use relatively crude and simple anomaly detection algorithms to compute for anomalies in line and be pretty much as fast as a batch anomaly detector. And the more sort of simplistic and fundamental set of algorithms that can do anomaly detection on that sort of data are a set of algorithms from statistical process control. We call them by the umbrella terms 3 sigma algorithms. And what they essentially involve is they look at any point in time in your time series, and they draw an upper bound and a lower bound of where they think the expected value for that networking data should be. And every time it goes far enough, 3 sigma above the upper bound or 3 sigma below the lower bound, there is an anomaly. So in this plot, you see like every time it went up above the expected bounds or below the expected bounds, it would have raised. So in this particular plot, it would have raised 2 distinct anomalies. Like you wouldn't know that it is actually a part of the same thing, but every time it would have spiked above or below the criteria, it would have raised an anomaly. The second type of algorithm, the category of algorithms for online processing is micro forecasting. So again, it works very similarly to the batch forecasting with like ARIMA and holds winters, but because it can't hold enough points in memory, what it does is it holds as much as it can and tries to forecast the next point. So the difference between it and the 3 sigma algorithms is the 3 sigma takes the point that it has now and tries to look back and see if it's anomalous or not. This one tries to look at the previous points, predict the next one, and then take the points from the future and see if it falls within its confidence interval or not. And the final sort of very easy, fast, and simple algorithm is histogram bins. And the key value here is that because you expect your anomaly values to be sort of rare, because anomalies are rare occurrences in your network, what you do is you bin the values into something that looks like a histogram. And the values that occur frequently obviously will bin into bins with a lot of values, and the bins that don't have a lot of values are therefore anomalous. So you can see here on the left you have a chart with some values between 4 and 6, and then all of a sudden you get a 10. And that will cluster into a bin with a relatively low number of values in it, so therefore you'd flag it as anomalous. And now Chet will go through some of the frequency domain stuff with you.
Hi. So one of the sets of algorithms that we use for actually extracting out seasonality from our volume data set is in the frequency domain. And there are a couple of different algorithms here that have been classically used in such as fast Fourier transforms, and specifically wavelet analysis has been used a little bit more recently. So the main goal here is to actually extract out a number of different frequency bands which represent various levels of information about the data set. So you can see here we have 3 different frequency bands, low, medium, and high, where low kind of represents your seasonality of the data. And it's a little bit more peaky, and it represents weekly and daily trends. So you can see that it goes up and down, where those vertical bars are anomalies. And once you get into the medium frequency, you can see that it's a little bit more flat. It represents finer grained trends, so on the hourly level, as opposed to the weekly or daily level. So that gives us a kind of an almost noisy signal in the high frequency, which is most of the trends have been extracted out of that. And you can see in this frequency band that whenever you get a spike, that's actually where your anomalies are. So those bars actually compress down. Those horizontal bars actually represent 3 standard deviations away from the mean. And you can see that once it jumps above that point, it's very easily to detect whether or not you have an anomaly. So here's an example over a full week of data. You can see that we have a kind of a daily trend that's going on here. It comes, like James said earlier, it goes pretty low in the mornings, and then it spikes up when folks are kind of coming into to work, and then it slopes back down. And on the bottom, you have the main seasonality of the data that has been extracted. The next level up is the mid-frequency band, where you can see more of the hourly level trends. And in the high-frequency band, you can see those spikes, which represent the anomalies, really begin to present themselves.
So from the implementation perspective, the online models are much simpler to implement than batch analytic models, so that's one of the advantages of using them. And what you need to do is again, you need to bootstrap your, collect enough data into a time series database to be able to either detrend or decompose the data into sort of the high, low, and medium frequency bands. Then what you do is you run MapReduce or Spark jobs over it to create this adjuster or decomposer so you can adjust the data in line. And what you do then is you funnel the data into this adjuster or decomposer to get it from something that looks like this to something that's more or less flat. And then you can have these online analytic, very basic online analytic methodologies, start learning on it, and then throwing your data into your persistent store, or your alerts rather, into a persistent store. So the next class of algorithms we wanted to go over with you is feature-based anomaly detection. And we're going to start specifically with continuous numeric features. And the algorithms that deal with anomaly detection on continuous numeric features basically all work on the data structure that looks something like this. So an example here is you have messages per second versus kilobits per second or kilobytes per second plot. Most of your values will sort of fall into the range where you see in black. There's a certain proportion of messages per second per kilobytes per second. And then some of them will be anomalous, or some of them would be sort of in a space on their own, right? So You either have a lot of messages, not a lot of data, not a lot of messages, or a lot of messages and a lot of data, right? So how do you try to make sense of it, and how do you actually figure out real time where you are? Are you in a point of normal points, or are you in a point of anomalous points? And so there are three sort of distinct algorithms to solve this problem that can both be fielded online. The first one is proximity-based technique, and the most popular one is k-nearest neighbor. So it's really simple to explain. So if you have a point in space, right, so you have a data structure like this, and you're trying to figure out where your next point fits, whether it's anomalous or not anomalous, and you try looking for that point's nearest neighbor. So you look, first nearest neighbor, second neighbor, third neighbor, fourth neighbor, fifth neighbor, and however many neighbors you look at. And then once you do that, you figure out, are most of my neighbors black or are most of my neighbors red? And it's as simple as that. And if they're red, you assign it to the red cluster. If they're black, you assign it to the black cluster. The second type of algorithms that you can use is your basic clustering. So the example of that would be k-means. And when you run k-means clustering over that kind of data structure, what it's going to do is going to come up with sort of a bunch of clustered values. So it might come up with one or more values for your large sort of black blob. But the main idea here is that the cluster with a lot of values are obviously not anomalous, and then the cluster with relatively few values would then be flagged as anomalous. And then the third type of technique is called the density-based technique, and it's sort of, it's very similar as well. So given a point, you see how dense is the space around you. So you look at your closest friends, how far away you're from them, and then, so if you do like, a value of 50, right? So you're relatively the red point is relatively close to 4 points that near it, but then the overwhelming amount of points, which is the black blob, are relatively far away from it. Where if you see the purple point, 50 of his closest friends are sort of clustered very close to it. So in that case, you'd flag the red or the orange dot as anomalous and the purple dot as non-anomalous. And the example of the kind of things you can find by using this sort of anomaly detection is you can detect port scans, you can detect denial of service, you can detect control anomaly detection or control traffic anomalies, right? And that sort of control traffic tends to have sort of very small packet payloads. And so if you have some sort of extreme anomalies where you have a lot of packets coming through with very low number of payloads, or you have only packets with high number of payloads, there's something going on. The control traffic going to your routers and switches and devices, sort of the proportionality of it is sort of not what it should be, so you can detect that kind of anomaly. Or you can detect sort of normal and benign behavior as well. So the second type of anomaly detection that you can key on is on categorical feature, because obviously not all of our features in anomaly detection are numeric. And the example of a categorical feature would be like a protocol that can sort of have a finite number of values, something like UDP, FTP, HTTP, or geometric area like Phoenix, Dallas, or London, or things like that. And so if you come from a software engineering background, that's basically an enum. It's the best way to explain it. And one of the best ways to alert on anomalies like this, or on features like this, is by using sketches, and particularly the count min sketch. So for those of you that don't know, sketch is sort of this probabilistic structure that, it's an algorithm that produces an approximate answer based on summary of the data stream in memory. And the obvious question is, why don't you just count as opposed to doing, probabilistic approximation of streams? And the reason is because a lot of the data, a lot of this categorical data is very large, right? So if you look at the number of values that a protocol can be, there's 42, believe it or not, 42,000 different values that variable can be. And for geometric area, there's 246,000 that value can be. And then let's say you have 10,000 assets on your network, and you need to keep track of each one of these values for each one of the assets you're tracking, right? So that very quickly becomes sort of a issue with scalability, keeping all that in memory. And so that's why you have to use a sketch. The trade-off is you're using a lot less memory and less CPU, but you're getting a probabilistic answer back. And the way we do it is we have categorical data streamed into this count min sketch, and the count min sketch counts the number of heavy hitters in your stream. So an example of that would be maybe like HTTP, UDP, like whatever. What are the most common protocols that you see on your network, right? So it extracts the heavy, the probabilistic number of these heavy hitters, puts them into a time series database. Again, generates the same table that we've seen again and again and again, where you have your some metric ID, the asset ID bin, and then the value for the heavy hitters. And then what it does is once it gets that historical data, it starts streaming the live data and comparing, if my expected value for heavy hitters is HTTP, UDP, FTP, DNS, and the actual what I have now is DNS, ICMP, HTTP, FTP. That is distinctly different from what I expected for that time frame. Obviously, I mark that as an anomaly. And you can do the same thing with geodata, right? So the metro region, or the combination of the two, the distribution of traffic to a specific geographic area as well. The next very useful thing to do with anomaly detection for feature-based anomaly detection is look at ratios. One thing about ratios, when something weird happens, they tend to spike either way up or way down. So they're very useful in looking at anomalies. One of the most useful ratios to keep track of is number of distinct elements divided by the number of total elements of a stream in a specific time frame. And the best way to keep track of that is to use another probabilistic data structure, another sketch, called hyperloglog. And hyperloglog gives you the approximate number of distinct elements in a multiset. Basically, you get the number of distinct elements, and then you have to divide that by the number of total elements. So what that looks like from the implementation perspective is you have a whole bunch of structured data streamed into your hyperloglog algorithm. You tell it what specific features you're interested in counting. So in our case, as an example, we're counting source port, destination port, source IP, destination IP. Now, for our specific implementation, we have it implemented in Storm. And because of how many numbers the Storm ball act a specific feature, we know what the total count for that feature is. So the hyperloglog gives us the number of distinct. The Storm balls gives us the number of total. We divide one by the other. We get our ratios. And then another trick that we do on the tail end of that is we stream that data into something called a digest. A digest is another probabilistic data structure that is designed is basically an online distribution. It's an algorithm for finding quantiles. And because we don't know ahead of time what ratios are anomalous and what ratios are not anomalous, right? Because is 0.9999 anomalous, or is it 0.99978? We don't know. And so by keeping this distribution, we're able to sort of think of it as a knob. We're able to turn it up or turn it down. And that sort of limits the number of anomalies we get out of this kind of scheme, because we don't know what the anomaly should be or what the threshold for the anomaly should be ahead of time. And it sort of gives us an ability to be adaptive in that sense. And again, the types of anomalies that you can detect with this kind of scheme is flash crowds. You can do failure probing and application hijacking, right? So when you're like the number of distinct, destination and ports, change, then, maybe like a certain application has hijacked it, like if the ratios don't match up. You can detect network scans and denial of service, right? So when, the number of distinct ports go way up, for example, the number of distinct IPs go way up, right? That's significant of a port scan. And depending if those are source ports or destination ports, if something is scanning you to trying to get in, or if it's even the worst case is something that's scanning from the inside trying to get out, right? So that means there's some kind of malware that's present on your system already. It's already got what it was trying to get, and now it's trying to get the thing out. So that would be a fairly serious kind of thing to detect. The final way to find anomalies is to look at correlations between different features. And the best way to do that is to look at entropy. And you can think of entropy as basically the measure of disorder in a stream. And the way you do that is, first you need to make sure that you have anomaly-free training set before you get started with this. And once you derive an anomaly-free training set by maybe having some people look it over to make sure there's nothing weird in it, you stream it into the entropy summarizer, and then produce a chart, an entropy chart by time bin. It sort of looks like a time series, right? So you do entropy for source port, destination port, source IP, destination IP. Looks something like this. Then what you do is you compute pairwise similarity between these different time series. And that's, to oversimplify it, is basically saying how similar the two features are to each other, how similarly they behave from the point of unpredictability with this entropy. And as you can see here as an example, the correlation between source IP and source port, source port and destination IP and destination port, they're very highly correlated. And what you then do is, once you know this historical information, you try to, you deploy a model, and you siphon out the real-time values from the entropy summarizer for that specific point in time, and you compare it to what your historical understanding of these similarities is. And what you do is, if they're different, then you know that something went wrong. Like, you don't quite know what, but you know that something is going on, right? Because if you expect two features of your data to behave the same way, and all of a sudden they don't, like, you don't know which one is off, but you know, like, there's something going on there. So you can't have a definitive alert out of an anomaly detector like this, but you can have what's called a reinforcement signal, that if something else detected an anomaly somewhere else, you can then reinforce that decision with something like this.
So can you guys hear me? The final class of anomaly detection algorithms that we have, well, it's one specific one, is principal component analysis, or PCA, which is a matrix factorization method that relies on single value decomposition. And it's typically used in machine learning for feature selection, right? So you have a very wide set of features, and you want to compress it down to a few subspaces that you really care about, because it captures the variance in the data. So the example that we have here is 3 different servers on a given week, the volume for those servers, and then the cumulative volume. Those are the 4 features that we're going to care about in this example. So the way that PCA works is it takes various combinations of those features, and it constructs a number of different subspaces that it cares about. So it takes basically a weighted value of each time bin, the numbers inside of that bin, and it multiplies it by what's called the loadings, and that's how the principal components are actually constructed. So in doing that, you're able to construct a number of principal components that have a varying amount of variance of the data that it actually captures. So what we actually have here are 4 different PCs that represent the volume here, and each one of them has various levels of importance attached to each one of the features. So you can see, if we were doing machine learning, and we obviously are, but if we were using it for the classical sense, these first 2 principal components would capture most of the variance of the data, and this would be what we would be using for prediction. But what you'll see in these last 2 or 3 components is the spikes that actually show up represent the anomalies. Because we're capturing most of the variance in those first 2 components, in those higher dimensions, you can actually see those anomalies pop up. So we have 4 different principal components that have been constructed from our volume data. They go from the bottom up. So the first one you can see kind of represents that hill trough pattern that we saw earlier. The second principal component has a little bit of that, but it's starting to get a little bit more noisy. And then once you get into the top 2, you see that it's mostly noise, and those points that represent the anomalies are really beginning to present themselves here as well. So principal component analysis is also a valuable tool whenever you're looking for anomalies in this kind of data.
So in conclusion, so putting it all together, this is an example of how we implement the whole thing on top of our framework called OpenSOC. And so as you can see here, it's sort of a 3-framework solution. So the first one is OpenSOC streaming, is where we take a whole bunch of data from as many telemetries as we can. We transform it, we enrich it in live, and we put it into a special Kafka topic called enriched. And from there, we pull it out with 2 distinct types of topology. The first one is the aggregation topology, and the main sort of reason behind that is it aggregates and summarizes data for all of our batch analytics. So it takes the summary, it takes 2 scriptable components, which is filters and aggregators. So you script them, to say exactly what it is that you need summarized. It summarizes and streams that data into a time series database for further analysis by MapReduce jobs, and then propagating the data back into a stream processor. And then the third framework is obviously OpenStack machine learning, which has a router which figures out which either volume of data or which features of the data that it needs to pipe to each individual model, whether that data needs to be decomposed or deserialized or deseasonalized, or if that data can be piped in as is. Then there's a scorer component, which is that supervised continuous improvement loop that I talked about in the beginning of my presentation, where it gets some results, then somebody looks at it, evaluates it, reinforces the training set, retrains the classifier, and then eventually reduces the number of false positives. And then out of that, that produces alerts either into Elasticsearch or Hive, or back into other external services that consume the data from our algorithms. And so that's pretty much it for us. Just wanted to briefly mention that we are hiring all across the board. So we're hiring data scientists, aspiring data scientists, and security researchers like everybody else here. We want them as well. And another thing we're doing is we're trying to put all of it in the book, because as we found out, the information about these techniques does exist, but it's not very digestible for normal people like us. So we had to do a lot of reading, a lot of Coursera learning. So what we really want to do is sort of just summarize it, make it easy for people to bootstrap themselves into some initial level of capability, so they can sort of build value on top of that, as opposed to spend 2 years, getting up to speed like a lot of other people do, and partially we did as well. And with that, we are done. We're about 1 minute over our little time slot, so I don't know if we're allowed to take questions. If not, we'll be here, so you guys can just come here and ask us a question. So I guess that's it. So I'm clapping to myself.
If you have any questions, the microphones are on the side, so you can.
Or you can just come up to us.
Can you tell us something about the scrubbing? Scrubbing, the last category you said you will say something to review the future methodology you will use.
Scrubbing?
At the beginning of the very first slide, you said.
Oh, web scraping. Yeah, so we're really early on with that. So one of the things that that I've done and seen in the past work well is you set up a service where you set up like a whole bunch of, and as an example would be, you set up a whole bunch of fake job boards advertising for specific technologies for specific customers. Okay. And then you watch the traffic as to,
okay, yeah, that's fine.
You look at the traffic as to which APT actually looks at the job ads, and then you sort of make a link between the type of APT that looks at customer job ads, and then you try to relate that to asset and adjust the thresholds for the models, based on that some internal factors. You can then tweak the internal models for each individual customer to adjust thresholds for alerting. So that would be an example.